Hello. All of you have heard about diffusion or diffusive processes of chemical species at this stage, you know that. What you still probably don't know is how diffusion can help save us from ourselves. Yes. On a daily basis, we hear about CO2 emissions from human activities that are contributing to rising global temperatures, right? And it is estimated that we're pumping about 40 billion tons of CO2 into the air each year. And almost 80% of this comes directly from fossil fuels. Well, some very clever scientists and engineers have been actively working in the past years on the possibility of converting unwanted CO2 into valuable chemicals like ethylene or fuels by using engineered versions of different catalytic formulations. So turning this unwanted CO2 into fuels and feedstocks not only turns a polluting waste product into something useful, but also reduces, of course, our reliance on the fossil fuels that are being generated in the first place. So one of the main problems with these catalytic systems that are under research is the low conversion efficiency, and that is why researchers are working on transforming more of the CO2 that flows through the system into valuable molecules. So it's actually here where diffusion will play a key role. If the researchers manage to engineer a more efficient diffusion process of CO2 from the process gas onto the catalytic surface, we could definitely say that diffusion will contribute to help save us from the CO2 that ourselves are emitting into the atmosphere, right? In particular, we have the so-called gas diffusion electrodes that are overcoming some of the issues by incorporating what it's called a carbon-based microporous layer, through which the CO2 diffuses much more efficiently before reaching the catalytic surface. And this catalytic surface is usually made of copper. So it's all about the diffusion and how we enhance the diffusion, the mass transport of the CO2 from the gas onto the surface. But if we really look into that process at a microscopic level, why is this happening? Well, diffusion, as you all know, is a mass transport phenomenon that causes the distribution of a chemical species, in this case the CO2, to become more uniform in space as time passes. So, if the concentration of CO2, for example, is initially not uniform, or in other words, the concentration of CO2 is greater in the process gas than over the catalyst surface, then over time diffusion causes mass transfer in favor of a more uniform concentration. Now, what is the value of such mass flux? How do we compute how many grams or moles or kilograms of CO2 are transported per unit area and unit time? Well, you will know that this mass flux by diffusion can be estimated using the well-known Fick's law. And this Fick's law, what we have is JD, which is the mass flux due to diffusion, and is equal to minus D, which is just a diffusion coefficient, which multiplies a concentration gradient, so nabla C. So this gradient is just how much the concentration changes over a distance. So this expression is going to give you, this Fick's law is going to give you the flux of CO2, or the amount of mass transported per meter square and second. And this number will represent or will give you an idea about the efficacy of the CO2 mass transport process. Another question we can look at is how long will it take for a CO2 molecule to diffuse from the gas side on the left to the catalyst surface? Well, the diffusion time can be roughly estimated as the square of the characteristic length of your system divided by the diffusion coefficient. We will see later in the course where this expression comes from. But for now, I would like you to kind of memorize or to note that there is a possibility for estimating. This is just an estimation. For estimating the diffusion time of a CO2 molecule, in this case, to diffuse from the gas side to the catalyst surface. What is a characteristic length? So usually the geometry of a system, of a physical system, is characterized by a characteristic length, and it's usually the smallest dimension in your system. So, for example, in a pipe, the characteristic length is the diameter, because usually the diameter is much smaller than the length of the pipe. In this case of the CO2 conversion, we could say that the characteristic length of the system is just the thickness of the microporous carbon-based layer. All right, and this, as I said, is the diffusion coefficient. That is something that you all have heard of in the past, whose units are meters squared per second. And this diffusion coefficient is just a measure of how quick a species diffuses through a fluid. So the higher the diffusion coefficient is, the quicker the molecule, in this case CO2, will be transported from the gas phase onto the metallic surface. So thinking back about this new catalyst to convert CO2 into valuable molecules, we can say that engineering the textural properties of the carbon-based layer can help to maximize the diffusion coefficient. And this is critical to kind of increase the conversion efficiency of CO2 into valuable chemicals. So far, we have talked about diffusive processes applied to mass transport processes. However, as you all know, this can also be generalized to this all can be generalized as well to heat transport. I guess all of you have performed, hopefully, a heat transfer calculation where you have estimated the heat flux. And by that I mean the joules transported by unit surface, meter squared, and unit time, second. So, as I said, all of you have performed a heat transfer calculation where you have estimated the heat flux by conduction, well, just using the thermal conductivity of the material, the temperature difference, and the material thickness, right? Now, just think again for a second on the similarities of these three concepts with diffusion: concentration gradient and distance. Indeed, we can conclude that conduction is a heat transport mechanism, as you know, but it's also known as heat diffusion, right? So rather than heat conduction, in this module, we're going to be talking about heat diffusion. In the same way that you have mass diffusion, we can have heat diffusion. Just remember that diffusion, the word diffusion, comes from a property gradient, such as the concentration of a species. But, of course, it also comes from temperature gradients. So from now on, we will talk, as I said, about diffusion as a mechanism taking place in both mass and heat transport processes. Of course, you can calculate the heat flux by diffusion using just the Fourier's law. So JD, which is, as I said before, flux by diffusion, is just minus the thermal conductivity K of the fluid times the temperature gradient, nabla T. Now, if you have a look at the diffusion coefficient units for mass transport, meters squared per second, you will see that they are different to those of the thermal conductivity, watts per meter and Kelvin. So, to make things easier, there is a way of defining a parameter called thermal diffusivity, with the same units as the diffusion coefficient for mass transport, meters squared per second. And then we will use the Greek letter alpha for this. Alpha is the thermal diffusivity of a fluid and can be calculated just dividing the thermal conductivity by the fluid's density and its specific heat capacity. This concept is very important, so please remember how to calculate thermal diffusivities from other thermodynamic properties such as K, ρ, and Cp. Likewise, for heat conduction, or from now on, as I said, heat diffusion, we can roughly estimate the time required for diffusion of heat across a characteristic length. How? Well, in the same way as we did for mass diffusion. The time required for heat diffusion is the square of the characteristic length of the system, the smallest one, divided by alpha, the thermal diffusivity. So obviously the time units are seconds in this case. Now, diffusive processes are not the only ones contributing to the transport of mass or heat. If they were the only ones, the transport of mass and heat would be extremely slow. Indeed, there is a second important mechanism which is called convection, so heat convection or mass convection. Convection in both mass and heat transfer is due to the bulk motion of a fluid. For example, the flow of liquid water transports molecules that are dissolved in the water. Similarly, the flow of air transports molecules present in air, including both concentrated species, for example, oxygen and nitrogen, and other dilute species, carbon dioxide and argon, right? So that's the transport by convection due to the fluid velocity. In these images, we can see convection in action. We have a figure in which we can see the concentration profile of a chemical species at time equal 1 second. And then below we have another figure of the concentration profile after 2 seconds of convection. Obviously, we can see that the concentration profile has been displaced by a vector, which is a displacement equal to the velocity of the fluid, u, multiplied by the time. So velocity times time is the displacement, right? Since the velocity of the fluid in this case is 1 meter per second in the x direction, this obviously corresponds to a left to right displacement of 2 meters. So the mass of a species like oxygen distributed in flowing air is displaced according to the velocity u. Therefore, in contrast to diffusion, there is no irreversible transport of CO2 between regions of high and low concentration, in the sense that the flow can be reversed to go in the opposite direction, so can mass transport by convection. Likewise, we can compute the value of the mass flux, this time due to the second mechanism, convection. So this mass flux by convection can be calculated using the concentration of the species times the fluid velocity, u. And similarly, we can talk about the heat transport due to convection, like density times Cp times temperature times the fluid velocity. If you check the units, because they are fluxes, they have the same units as the fluxes due to diffusion: kilograms, moles or grams per surface and time, and joules per surface unit and time. So in conclusion, the total flux of either heat or mass transport is just the sum of their diffusive component plus the convective component. And now, this is the last thing that is very important. Is there any way to determine which of these two mechanisms, diffusion or convection, is governing the transport of mass or heat? Which is more significant? Is there a more significant transport mechanisms or not? Yes. So for this, what we use is the dimensionless Peclet number, PE, which is just the ratio between the transport due to convection to the transport due to diffusion. So for mass transport, the Peclet number is calculated as velocity times characteristic length, so the smallest one, divided by the diffusion coefficient. Whereas for heat transport, the Peclet number, or also called thermal Peclet number, is the velocity of the fluid U times the characteristic length L divided by the thermal diffusivity alpha. If we calculate this Peclet number for a system, it will tell you which of these two mechanisms, diffusion or convection, is governing the transport. So if the Peclet number, if the order of magnitude of the Peclet number is much smaller than 1, so 10 to minus 1, minus 2, minus 5, that means, if you have a look at the ratio, that means that the diffusion is more significant, right? So we can neglect the convection effects. However, when the Peclet number has an order of magnitude much larger than 1, that means that the convection or velocity of the fluid is controlling the mass transport or the heat transport process. Don't forget how to calculate Peclet number. This is very important. We will use this throughout the whole module to determine whether the effect of convection is important when the Peclet is much larger than 1 or not when the Peclet number is much smaller than 1.